Hi, this is Mrs. Hedden with another video, Heat and Temperature Notes 5. We're going to start out with a major correction. In a previous video, I gave an analogy of the bonds being springs. It was a bad analogy, it was misleading, and basically I was just plain wrong. So I'm going to try again with a different analogy for exothermic and endothermic reactions. I'm hoping that the video from MIT helps straighten things out also. Let's consider kinetic energy for the phases of matter. Well, which phase is the greatest kinetic energy? Solid, liquid, or gas? Well, that's easy. In molecules, a gaseous state move around much more than solids or liquids. Therefore, gas has the greatest kinetic energy. So if we look at it from that viewpoint, energy must be added to the material to increase its kinetic energy to move from solid to liquid to gas. Therefore, movement in that direction absorbs energy from the surrounding area, making it endothermic. Energy is entering into the material. Again, I have a bad memory that endothermic and entering helps me. Likewise, to move from gas to liquid to solid, energy must leave or exit the material. Movement in that direction is exothermic. Again, this is just an analogy. It's not a complete nor totally true story. Bond energy is involved. Things get very complicated. But it's a reasonable way to remember and evaluate what's going on. If we're going from solid to liquid or gas, we have to add energy because those later states have more kinetic energy. Going from gas to liquid to solid, we have to remove energy because those states have less kinetic energy in them. Let's see. So let's go here. Energy must be added. So when ice is used to cool a building, like they talked about the MIT thing, it moves from the solid stage, which is ice, to the liquid stage, which is water. In the process, it must have energy added to it, which, thanks to the conservation of energy, means that energy left the surrounding area or the building. That lowers the building temperature, cooling it down. Likewise, when you sweat, liquid is moving from the gaseous state and absorbs energy to do that. So it cools down the surrounding area, which happens to be you. A great resource for thermodynamics as well as other things is the physics hypertext. And from that, I got some scattered thoughts. Under extreme conditions of heat and exercise, an individual may sweat more than 1 liter of liquid per hour. That's a lot of liquid. No wonder athletes need to drink a lot. In terms of cooking, the interior of roasted meat can never reach temperatures higher than the boiling point of water because all that energy is just going for a phase change. But when the water dries out, at that point the meat immediately goes to shoe leather. The outside, where the water evaporates quickly, is quickly dried out, which is why your outside gets that nice crust on it. Okay? And the inside stays hopefully nice and pink. Cocoa butter is unique among the fats. It's very regular in composition. Most fats are actually mixtures. This gives it a very definite point where it has a definite melting point, which is unlike butter. Butter kind of gradually melts down. Okay, as cocoa butter melts in your mouth, it goes from solid to liquid, which means it's absorbing heat, going from a lower energy state to a higher one. That's what makes chocolate bars taste cool. And then again, there's some other stuff if you like to read it. Let's talk about my surgery Tuesday, which went fine, although I've got a big casty thing on my hand. But the bad part, the worst part, was for the 12 hours preceding it. I couldn't eat or drink anything. I'm okay not eating, but that meant no cups of morning tea, and that was not cool. After I got home, I was immediately ready to have a good, large cup of tea. I make the tea with boiling water. I brew it for 3 minutes. It cools down about 3 degrees. We've checked it with thermometers. And I wasn't going to wait any longer. I was already 2:30 in the afternoon. In order to get it cooling down even more, at 85 degrees C, if I waited a couple of more minutes, it's still hot enough to cause third-degree burns, which is not a good way to enjoy a cup of tea. So I add ice cubes to it to make it a more drinkable 55 degrees. It doesn't taste quite as good when I add the ice cubes. It waters it down some, but it's still tea and has all the wonders of caffeine. Okay, so how many 23.5 grams of ice cubes straight from the freezer should I add to my rather large cup to bring it down to that drinkable temperature? Well, first you got to write down everything you know. We got the initial temperature of tea, the final temperature that I want it at, the volume of tea, which infers, because tea is basically water, flavored water, that the mass is 355 grams, and I got the mass of the ice cubes. And what I want to know is what is the mass of the ice. Conservation of energy says the total energy must remain the same. So the heat gained by the ice in the melting must equal the heat lost by the tea. Or, to put it like that, the positive Q ice must equal the negative QT. But it's a little more complicated. The ice must first warm up to melting temperature, then have a phase change, then warm up to thermal equilibrium with the tea, per the zero law of thermodynamics. So we get something like this equation down here, which I then translate into formulas. MC delta T of the cold ice, ML, L fusion of the melting ice, MC delta T of the ice that is really actually not ice anymore, but water. Warm water, but water and I'm the same, is equal to, and I should have the negative sign in here, negative MC delta T. Okay, looking at it some more. So I've got this big long equation here, and here I did put in the cold water, and we're looking for latent heat of fusion. We put in the substitutions. So I looked up the specific heat of ice, which is different than the specific heat of water, by the way. I've got the differential temperature. It was the final 0 minus a negative 18. That's where that plus comes. The mass of the ice times the specific heat, the latent fusion of ice, water, and then the mass of the ice times the specific heat of water now. The difference in the temperature, I'm going from 0 degrees ice to 55 degrees, where I want my thermal equilibrium, my teacup at, the mass of the tea, the specific heat of water, and the difference in the tea. Again, my final temperature minus my initial. Throw them all together. Notice I have kilojoules over kilograms. I have kilojoules on this side, so I don't have to worry about that 10 to the third because it's on both sides. And I get my mass of ice is 0.074 kilograms, which doesn't really tell me how many cubes, so I divide that by 23.1 grams, and I get about 3 cubes. I think it's really 3.2 cubes, but who's going to chip off 0.2 of a cube? It'll get that tea to a low enough temperature where I can drink it. And so this is a more complex problem, which involves the specific heat of ice first, and getting that ice up to melting temperature, the actual melting Q, then the specific heat of water, getting it up to that equilibrium, all equaling this. And notice I have this negative sign in here because this guy is, let's go back a second. I didn't have to go back. This guy here, the heat gained by the ice must equal the heat lost by the tea. So this is a loss, so that's why the negative sign is in there. Alrighty. You have another web assignment tonight, due tomorrow at the start of class, and you have problems from the next sections. All those problems are going to be due Wednesday, the day of the test. These problems are here: 57, 59, 63, 73, 74, 75, 77, 83, and 85. And of course, tomorrow, over the weekend, you'll have another web assign with an assortment of these problems. It'll be a longer web assign. It'll be over the weekend. Thank you very much for your time. Until tomorrow, adios.